activity causes it to be released. Unless human activity causes this stored carbons to be released. So it is believed that when you store it in such a location, it can be stored for a very long time. And that is why carbon crediting, carbon offsetting is now trending. It started with carbon, is it a carbon credit mechanism? I've forgotten the name. Carbon credit mechanism. Yeah, that's where it started with. So CO2 sequestration requires 3 steps when dealing with carbon dioxide. First, you have to remove it from the atmosphere. Then you transfer it to plant biomass. Then from the plant, we bury it in any of the pools, the larval pool. So you remove, you transfer, and you store. Those are the 3 steps: removal, transfer, and storage. So this is a pictorial how it is done in the atmosphere. So the carbons are carbon dioxide are removed by the biomass through photosynthesis. Then the plant biomass transfer it to the soil for storage. So this is a pictorial view of how it is done in the atmosphere. And the sequestration of carbons can be stabilized by 3 major ways or mechanisms. We have the physical mechanism, where carbons are isolated within the soil microbes and macro aggregates. And we have the chemical mechanism, where they are bonded and absorbed to clays to prevent biological consumption of carbons. And the final one, which is the biochemical. So here there's resynthesis of carbon, and it may result from the formation of intricate molecular structure that impedes the breakdown of what has been stored in the soil. So after the removal, the transfer, and storage, this mechanism helps to stabilize it so that it won't be easily lost from the soil. And factors that affect soil organic carbon sequestration are: number 1, the soil properties. The soil properties, because for it to be stabilized, it needs a condition that will not allow easily breakdown. So the soil property is one major factor. And the second one is the climate conditions. The climate conditions. Yesterday we mentioned the temperature and precipitation. Because moisture is needed for decomposition activities as well as the temperature in the soil. And the third one is the land use and management practices. The land use and management practices. So for the soil properties, soil depth, soil type, the texture, composition, pH, soil climate, the temperature, that's the temperature, rainfall, all these affect, they are the major components up to soil pH. The remaining ones influences what we have now. Then for how does climate change affect the soil carbon stocks process? Research has shown that projected changes in soil carbon, there is a projected changes in soil carbon under climate change. They vary from small losses to moderate gains. So as climate is changing, soil organic carbon from models would change from loss to gain, depending on the changes in the climate. And accurately estimating the combined effect of climate change on soil is challenging because our models, as we learned from the section 2 yesterday, are not even accurate. There are uncertainties. And so this makes it a bit difficult to accurately say that this is what will happen due to climate change. And some of the natural soil carbon sequestration processes, such as plant litter decomposition, roots, exudation, and microbial activities, they lead to soil carbon sequestration. And these are natural processes. The litter decomposition, they are natural. If you have the forest, you don't do anything to it. It takes place naturally. But because now we are influencing the activities, the natural processes need to be enhanced or facilitated so that we can catch up with the anthropogenic activities. And climate change affects these processes. For instance, precipitation and soil moisture. If rainfall in our rain-fed system controls most of the activities in the soil in the rain-fed system, then climate change influencing precipitation would affect this process, this natural process. And also temperature. Temperature affects decomposition, as well as vegetation and land use changes. And so it's natural, but now being affected by our anthropogenic climate change, as has been certified by IPCC. And some of the anthropogenic soil carbon sequestration processes are the practices like the conservation tillage, cover cropping, agroforestry. They help promote carbon sequestration. And the effectiveness of these practices may be influenced by climate change related factors. So both the natural and the anthropogenic are being influenced or affected by the current climate change situation. What are some of the feedback mechanisms in this? Now, when there is increased carbon loss from soil, it increases the concentration of carbon dioxide in the atmosphere. And this exacerbates the greenhouse gas effect. So if what we have in the soil is being released to increase the amount of carbon dioxide in the atmosphere, then it means we are taking our, what do we call it? Is it a green? Yeah, the green layer. The green layer that is preventing radiations from returning back into the atmosphere. And changes in soil moisture and temperature conditions also affect plant species distribution and growth, which will invariably affect the composition, as well as even the storage and stabilization of carbons that has been transferred into the soil. So climate change has a lot to do with soil carbon sequestration. And what are some of the techniques for sequestering carbon in the soil? Some of the techniques. So soil carbon storage can be influenced by the management practices of farmers. And if, for instance, we boost carbons in the soil or carbon in the soil, it will help boost crop yield. It will help boost crop yield, and also applying carbon from outside sources, and it will help reduce carbon losses. The management practices is also a key factor. Besides the soil types, the climate, management practices are very important if we can maintain what we have in the soil or even improve it. So some of the techniques for sequestering carbon in the soil through effective management practices are they include management to increase crop yields, tillage and crop residual management, crop rotation, pasture and grazing management, and the addition of organic matter to the soil. Most of our farmers are now adopting that. and also adopting alternative farming systems like agroforestry, and there are a lot of them. Yesterday, I referred to the second section, we were introduced to some of them as well. And some of the other techniques, specifically for carbon sequestration in soil, is conservation tillage. Conservation tillage, where we reduce the turning of the soil and improve crop residual retention. So farmers are advised, when you harvest, you leave the residue on the farm and you don't till it. So as it decomposes on the surface, it increases the organic matter composition of the soil, thereby improving the organic carbon content. And also adopting fallow and crop rotation, fallowing and crop rotation, as well as changes in land use practices, like I've talked about reduced tillage under conservation tillage, then reforestation, intercropping, and also pasture management, especially for livestock areas in the Sahara where we have major livestock production. Pasture management is important, and irrigated systems, adopting irrigated systems and organic farming systems. These are key practices if we want to sequester carbon. And we can also use recycled organic materials and composting. We adopt composting and biosolids. Composting and biosolids, they also help to sequester carbon to the soil. This section is a practical section. And because of our time, since we will be taking the fourth section, this is a practical section that will be on the course. Is on biochar, how to make biochar from cocoa pod husk. Because of time, I wouldn't go through it, but it's a step-by-step approach. So anybody who will be taking the course can be taught. It's a practical session. How it will be done. So I'll end here so that we can take the questions in the remaining 10 minutes for the fourth session. We also use the remaining 1 hour. Thank you.
I think there are some questions on the chat and also on the Q&A.
Okay.
Hello.
Hello.
Yes, we can hear.
Yes, Francis is my name from Uganda. Thank you so much for the elaborate presentation. I just wanted to know, in terms of ranking of the practices that helps to sequester carbon in the soil, if you were to rank, which ones have been found to be more effective in terms of the carbon sequestration effect or effectiveness? Thank you.
Okay, so thank you. Please, are you referring to the number of the options presented in this slide? Hello? Hello? Oh, global.
Maybe let's stick to the global.
Okay, well, if we got you right, you wanted to know the options, practical options, among the practical options for sequestering carbon, which one appears to be most effective?
Yes.
As a matter of fact, application of biochar tends to be in the simple sense that, you know, biochar converts the carbon neutral process of organic matter decomposition into a negative one. And if I can put a step there, you see that plants, every carbon that a plant takes is from the atmosphere. And then when the plant dies, it returns a bulk fraction of the carbon it took from synthesis back into the atmosphere. So it makes it neutral. It takes all from the atmosphere, eventually it gives virtually all back into the atmosphere. But when you convert it to biochar, and then you apply it to the soil, then you divert, you change the equation from being a neutral one to a negative one. And therefore, you are now increasingly reducing the amount of carbon that is in the atmosphere. Because once the plant uses the carbon to synthesis, and the product becomes biochar, the carbon that comes from the atmosphere into the plant is locked up in the lithosphere or in the soil. It doesn't go back. And so as the cycle continues, more and more carbon are being fixed in the soil. It's actually estimated that biochar production, if it is effectively done, can contribute to about 12% reduction in global greenhouse gas emissions. I mean, regards to carbon. So biochar alone can reduce the amount of carbon emitted from all sorts of processes into the atmosphere by 12% if it is effectively done. So for me, it is the most potent one. And the other option also is that since it's like production of fertilizer, you have the freedom to control the amount that is produced and so the amount of carbon that is fixed. The more you produce and the more farmers apply, the greater the amount that is. So with biochar production, man has upper hand in manipulating the process, and therefore it seems to be the most feasible and potent option for greenhouse gases. Thank you.
Thank you, Dr. Poku. Your answer well understood.
Thank you, Janvier. This is Janvier.
I will do.
Okay, thank you. Any other question, please?
I have a question.
Yeah.
This is Rosemary from UCU in Uganda. I have an inquiry. Does carbon sequestration and some of the practices that farmers do, like you've mentioned, biochar, does it count for carbon credits? Are there efforts to count that for farmers who are already taking part in some of those practices? Thank you so much.
Yeah, so
Okay, thank you. When carbon crediting started, the focus was on afforestation and other practices that land restoration. And so if you do carbon biochar, mostly that one is not counted, because for the verification, they will check the trees that you have on the field, their growth, and they will estimate the amount of carbon per the age of the tree to determine the metric tons of carbon dioxide they have to pay you. But when you do biochar and you add it to the soil, that cannot be verified easily. So it makes it difficult to be considered in the carbon crediting. Carbon crediting is basically afforestation and restoration of land. And the restoration of land is determined by what you are now going on it. So
thank you. Thank you, Rosemary. I'm on the same page with Dr. Bessa. You know, the challenge with application of biochar is that it's farmer managed, and therefore it becomes extremely difficult to verify whether the practice was done first of all, which feedstock was used, the quantum applied, and the consistency in the application. If you apply one season because you planted an annual crop, and so you estimated the quantity for that crop, and the rest of the season, nothing is going into the soil. You know, it becomes very complicated. So for now, I do not know of any place where if a farmer intensely into biochar application has qualified for carbon crediting and is therefore considered as an offsetting program. Thank you.
Thank you so much. I think we need to do some more research into that. There may be opportunities to add it, but thank you so much.
Yeah, thank you.
There are some
I have a
questions.
question.
You have a question,
Please.
okay.
How would you differentiate between the soil organic matter content and the soil organic carbon stocks?
Okay. So you want the difference between soil organic matter?
If I'm explaining to a student, how would I tell this is soil organic matter content and stocks? Because the practices you recommended for improving the stocks are the same as the soil organic matter content.
Thank you. Please, may we know your name?
Sorry?
May we know your name and
I'm Joyce. Joyce.
From please.
From Kenya.
Thank you, Joyce. Okay, Joyce, first of all, soil, organic carbon and organic matter, they are very related. It is every organic material is largely made up of carbon, hydrogen, and oxygen. These are the building blocks of organic units. So it is the carbon in organic matter that we talk about when we are talking about carbon stock. The only difference here is that if you estimate organic carbon as is routinely done in our soil labs, then you multiply by a factor, which is 1.724, then you are able to estimate the amount of organic matter. It is largely because about 50%, about 58% of organic matter is carbon. Carbon is the most dominant element in all organic materials. So that is the chemical relationship that exists between organic matter and carbon. See, in other words, I'm saying that carbon is a subset, a smaller member in the bigger organic carbon. But when we talk about stock, we do so with regard to a certain depth. So let's say they are 15 centimeters. We are interested in knowing the total mass of the total weight of carbon, organic carbon that is stored in that depth of the soil. So you see that in that case, you find the percentage carbon from the lab, and then you try to estimate the quantity that is in the soil. Is that okay?
Yes, thank you very much.
There are some questions from the chat. Maybe quickly we'll go through. Oh, I've seen a hand.
Yes, yes, I have a quick one here.
Okay.
In relation to carbon credits.
Okay.
Many times we talk about afforestation programs, which were highlighted earlier. But I also see that we have issues with the plantation crops that stay on the land for a long time. I'm from Uganda and I see cases of coffee, cases of bananas, which stay for a long time. What is your experience worldwide on such crops, including because when you look at their lifespan on the ground, some of these plantations have been there since the times of our grandparents and they are sequestering carbon, but do we have them in line or they are off the items? They are taken as crops. Thank you.
Thank you, Augustine. Some of them are considered, and it depends on, as I said, the standards vary. Like for instance, under the Red Plus project, there are certain institutions that determines what can be added and what cannot be added. So for instance, if you have a cocoa farm, Ghana, most cocoa farms with trees are being considered. If you have a cocoa farm with certain number of trees, it could be considered. But if it's purely plantation, and you know, plantation, you can decide to cut it down and change whatever you have there for another thing. So, and also, if you want to use your plantation, it shouldn't be something that is already existing. I don't know much about that. It should be something that you are starting with them. So they verify it, they start the process with you. they start it with you, they can now take baseline data, then they can, with time, they'll be verifying and calculating for you. And I know I've been in contact with those who are doing this in Ghana, and they have a lot of information about it. And I'm sure in your country too is there. But I don't know much about existing farms, how they do it. Most of the ones I know in Ghana, they are new farms. They are being established purposely under that project.
Okay, I'd like to add a point to this.
Augustine.
Okay, Augustine, you see, the issue is quite sensitive and it involves money. So the key point here is that existing plantation carbon negative? If it is carbon negative, then it can qualify for carbon offset. You know, it's not every plantation that will be carbon neutral or carbon negative. If you grow your crops and you don't add any materials which will contribute to carbon dioxide emission, and that the plants are absorbing and decaying and returning everything, that is neutral. But where you are into, let's say, severe organic agriculture and you are pumping so much manure onto the land, then in addition to the neutral cycle, from the plant side of the equation, the manure input is also contributing to massive greenhouse gases emission, carbon dioxide and methane, all going into the atmosphere. So then you see that this plantation, because of the large amounts of organic matter added, becomes carbon positive. And a carbon positive plantation cannot qualify for an offsetting program. That is the main reason why the programs certifying farms or plantations for these offset programs would want a farm or a plantation that is designed on purpose for the offsetting program, so that the standards are met and that a farm that is carbon positive is not mistakenly taken to be carbon negative or neutral. Okay, please, do you understand my point? Hello?
Yes.
Now I get you right. Thank you. Yeah.
If there are no more questions, I think we're going to ask about wildfire.
I'm the one to put the questions in the chat. The 4 questions is
okay. But I'm sure you've gotten your answers through the presentation.
no, I did not get the answer to the presentations because, for example, I was asking about wildfires. These days we are hearing about thousands and thousands of hectares that are going into fires, and I just wonder if that does not have any impact on soil carbon sequestration because of the drying the soil moist, maybe killing the underground vegetation, things like those. Do we account also that in calculating the greenhouse emissions? That's first. And second, I was saying those countries who are the big emitters are also the ones who have the means to hide. Who controls and how do we control that the reporting is accurate and corresponds to the real emissions?
Yes.
And finally, I was asking also if when measuring the soil organic carbon, don't you think that resources may be also among the challenges, mainly in low income countries? Lack of, we don't have human capacities to doing that. We lack resources, like equipment. We lack money. Don't you consider that is a serious challenge in the measuring?
Okay, so starting from your last one, you are right. That is why it says that poorer nations lack resources, both human and financial resources. And that's the reason why soil monitoring networks are not being established in those locations. So that's why you are right. And the next one on the verification and reporting. Yes, although most of these organizations that are in charge of the verification and reporting are based in those nations, We still have our representatives when we go for COP meetings, those decision meetings. So it's not only them. They propose, we agree to it. As you are saying, it could be true, it could not be true. But as far as we are signatories to those treaties and policies, they didn't decide for us. We are part of the decision. It's not only us. And your first question on wildfires, Dr. Opoko would address.
Okay, thank you for your question. As a matter of fact, whenever organic materials burn, the carbon in them becomes carbon dioxide. So from that standpoint, every tree that is set on fire emits carbon dioxide. The smoke that is seen is largely carbon dioxide. So to be honest, wildfires are potential sources of carbon dioxide into the atmosphere. Therefore, wherever it's happening, it is contributing to severe carbon dioxide emissions. And then, for instance, so if you had a farm that or a plantation that could be used for a certain program, and for one reason or the other, it's bent, then you see that from that moment on, you are no more offsetting carbon, you are rather contributing to carbon. So it's a big problem. It's a big problem. Wildfires do emit carbon dioxide. Okay, please,
are you considering only the fires, the carbon that is coming out of fires, or also the problem that is coming as a consequence of those fires? I mean, all the dust, all the underground vegetation that goes off into fires, the heating of the ground, all that. Do they also have I suppose that they also have an effect on sequestration, right?
Yes. Okay, I get your point. So it is a multidimensional problem. You have the climate change or the global warming potential effects as one side, and then the loss of fertility or whatever happens down there with respect to microorganisms, native organic matter, and other things will contribute to cause a decline in the fertility. There's also the possibility of getting ash. You know, when wood burns in the open air, the end product is ash, and the ash is sort of a nutrient input, and because it's very rich in minerals. All the minerals that the plant absorbed will be, at the end of the day, after the burning process, will be in the ash, which will be added to the soil. So, but largely it's a very negative process, or it contributes, it adversely affects everything. Because the quantum of ash that is added per se would be sufficient fertilizer to enhance the fertility of the land. So that side also it has an adverse effect. It will adversely affect the fertility, it will adversely affect the global warming potential, and then the health of the indigenous living nearby. Yeah. So I guess the best is the way around the problem is for the fire not to come at all. Because if it comes, it's not a good thing for everyone. It doesn't contribute any positive thing at all, regardless of the direction you may want to look at it from. That's my take. Thank you. Okay, please, are you there? Yes. Hello.
Yes, I'm good. Thank you.
Yeah, thank you too.
So, David, we want to continue from the sports section, session 4.
Yes, please. Yes, I think because of time, let's get going so that we can cover the last section.
Introduce yourself.
Okay, I'm Dacosta Asare, a member of the team, and we will be considering the 4th session, which based on spatial estimation and modeling of soil organic carbon sequestration. And at the end of this section, we'll be looking at measuring and monitoring of soil organic carbon using geospatial data and techniques, and also modeling of soil organic carbon using empirical and process-based approach. With the subsection 4.1, we are going to look at remote sensing and GIS of soil organic carbon measurements. Before we can measure soil organic carbon and model them, there are some components which we use remote sensing data and GIS techniques to aid our activity. So mostly we look at the design of soil organic measurement plan and also remote sensing of environmental variables that has been spoken of: climate, temperature, rainfall, vegetation, land use, land cover. All these are variables that contribute to soil organic carbon that can be also measured. And the 4.2, as I mentioned, we'll look at the modeling approaches. These are the delivery mode of this section. And also assessment will be done through presentations and exams and field reports. Some of the learning materials we'll be using, we'll be needing any computer, either desktop or laptop, which can run GIS and remote sensing softwares, which some example are the Quantum GIS, ArcGIS, and R. Handheld GPS or mobile phones can be used in also picking sample locations and the others as seen on the screen. These are some reading lists to aid our understanding of this section. With the measurement, Dr. Beza has spoken at length about that. I'll briefly go through some measurement plan, which before we can assess soil carbon, these flow chart can be followed. The first is assessment of the boundary in which you want to consider the assessment, whether within a basin, within a farm area, within a district. So we can have a local and also global base. So the physical boundary has to be delineated, and these can be done on the field or sourced from other secondary data sets. For example, if we are looking at a district based, we can get a district shape files to delineate our boundary. If we are looking at within a water basin, we can generate or delineate our watershed area to use for such measurement. So typically, this is how sometimes layout can be done. You can have your entire boundary and you delineate your project area and also areas that you will be estimating your carbon. So this is an example of a carbon project showing the area that is going to be estimated, and it can be divided into several zones. After the delineation, we may have to also stratify our site. This stratification is done where there are several factors that can affect it. For example, within a project area, climate or topography may not be the same. We also have different vegetation characteristics and soil type, and as well as management practices. All these affect carbon, so we can stratify them based on these variables. And these can be done with the help of remote sensing data set, which may include satellite data and aerial imagery that can assist us, and also aerial photos. And these can be done on a very large scale, global and also regional scales. So we will later look into how to sort all these data sets remotely to help us in our classification. Also, sampling design has to be performed. And in performance of the sampling design, we will look into areas where we can get insight into the population or the structure that has been selected. So typically, we can be using grid sampling, we can be using Transect for our study area. We can also do random. So with GIS, these can be planned on a desktop before visiting the site. Mostly it's advisable that field teams sampling can be done before visiting the site in order not to introduce bias in our sampling. So here we use GPS to record areas where we are picking the sampling. So if for homogeneous field, we can have the grid systematic sampling where a grid of about 10 to 100 meter grids can be calculated using a fishnet in GIS, and it can be also done randomly or using a transfer. One is heterogeneous, where we have several structure that has been displayed. We can also use these 3 methods of sampling to delineate and use for measurement. In terms of assessment, this is when we will be doing an assessment over a period. So as Dr. Besa said, mostly IPCC advocate for a period of 20 years, but effective ones, we can be looking at 5 to 10 years so that we can repeat this measurement. So now let's look at some principles behind the remote sensing of these data sets that we'll be needing in order to measure or monitor our soil organic carbon. So remote sensing technology, mostly through satellite-based or airborne platform, offer a valuable approach for collecting diverse information to help us in soil organic carbon systems. And basically, there are 3 categories where we can apply this method, or we can use to incorporate a method for quantification of soil organic carbon. The first has to do with direct estimation and mapping of the soil organic carbons. The second has to do with one which is being done by field sampling and laboratory analysis. GPS locations are stored, and statistical or regressions are being performed on them. The second has to do with capturing vegetation characteristics over the land surface using remote sensing products. And these ones are mostly used in the process-based carbon models and also land use management, where we are assessing the land use changes and farming practices, which can be incorporating our process-based model. So with this, these are some recommended remote sensing techniques, and also the type of observation that is being done and the objectives, and also to the skill level at which we can collect these data sets. So mostly, when we are dealing with small areas, farm lands, we can be using UAVs or drones and satellite to send some parameters of the soil to help us in our estimation. So we can be sensing soil moisture and some other nutrients to help us in our direct estimation. And with the measurement of vegetation indexes, we can also leverage on drones and also satellite images. But when we are looking at a very large area where we are monitoring the land use changes and management practices, we use solely satellite-based images. So remote sensing has to do with the act of sensing an object or an area or phenomena without coming into contact with the object. And in that, we acquire data which we can talk about spatial, spectral, and also temporal. This technique is based on sensing electromagnetic radiation, which is being emitted to the Earth. And these energies is being reflected, some are being absorbed, some are being refracted into the atmosphere. And we have sensors in space which are able to collect these energies which are being radiated. And on board these sensors are platforms. So some of the platforms can be aircraft, can be UAVs, or satellite platforms which are in space. And with the sensors, we can have cameras or scanners. So mostly the UAVs or drones uses cameras as their sensors for collecting these electromagnetic energy. So this is how it occurs. And once the sun radiates this electromagnetic energy, and it reaches through the atmosphere, it reaches the surface of the Earth, different features on the Earth react differently to this energy. So when it's being sensed, we use the different interpretation to also classify or analyze the data that we are receiving. And in the acquisition process, once the energy has been sensed and it's being reflected into the atmosphere, all these sensor platforms can store the data. The data can be stored as a numerical data or a pictorial data, which later can be visualized or interpreted. Once it has been interpreted qualitatively or visual inspection, some information products can be also derived from, and users as farm managers, as researchers can also use in decision making. So the platform that is being mostly used, we have the ground level platform, we have the area platform, and also the space-borne platform. So mostly the ground level goes up to about 50 meters, where we can be using cranes and handheld control. So we can have a mobile hydraulic platform where sensors are on board to sense vegetations within a farm area. We can also be using the field spectrometer to also sense certain kinds of vegetation or soil information. The area platform, which goes from low to high altitude up to about 50 kilometers, we can be using balloons, drones, or aircraft. On board these aircraft or platforms are sensors to be able to sense all these electromagnetic radiations for analysis. We have the space-borne, which goes very up to about 36,000 kilometers up space, with these sensors or platform was also revolving around the Earth. Some are stationary. We have the polar orbiting satellites, which orbit around the poles and has a reverse time. We have the geostationary, which orbits and rotates as same as the Earth. So an observer from the Earth will see this satellite as being stationary. And this is mostly used for material data collection. So with the sensors on board this platform, we have two main types, the active sensor and the passive sensor. The active sensor mostly use artificial source of energy, where the sensor produces its own energy, emits radio waves or light detecting waves to the surface of the Earth. This is very efficient and it can be used both day and night and in all weather conditions. The other passive, which uses the natural source of energy from the sun, can only be acquired during the daytime. And mostly we use the imaging radiometer and spectrometer sensors. And the active sensors are mostly the LiDAR and the radar. These sensors provide some imaging systems. So the passive is able to provide us with multispectral data or imaging system. We have the hyperspectral data and also the thermal data. So the hyperspectral data is able to take a very narrow wavelength within a very long span of data sets, while the multispectral picks certain portions of the electromagnetic wavelength and is being recorded. So this illustration is being depicted down there. We have the thermal imaging system that is also able to store radiations or interactions within the surface of the Earth, also as infrared radiations that are being stored. Within the active imaging system, we have the radio detecting and ranging. We have the light detecting and also ranging. These imaging systems also have its own applications. With the radio, it sends radio waves or pulses to the surface of the Earth. It bounces back and is being stored for analysis. And this can be done, these sensing systems can be done in the daytime or the nighttime. And it's mostly used for flood analysis and imaging the activities of the Earth. The LiDAR is mostly used for digital elevation to get topography of the data. Each point provides us with point cloud data, which are in 3D space. You can get the X and Y and also the height information from LiDAR data sets. Now let's look at some overview of these satellite missions that we have been talking about. So they are broadly largely some data sets or satellite missions in space now that we can leverage in sensing information, environmental variables to aid us in our soil carbon measurement, monitoring, or assessment. So we have some which are mostly local or regional scale, and we have some for global scale analysis. So these are some of the missions. We have the popular ones, the Landsat mission, the Sentinel, the Planet Labs, the ASTA digital globes. Some of these sensors, especially the Spot and digital globe, are not free. There are some which are also made free available to the public, such as the Landsat and Sentinel. With the Rapid Eye or Planet Lab provides a planet scope image, which is of very high resolution to about 3 to 5 meter resolution, which can be requested for educational purposes. We also have the MODIS, the very high resolution. We have the SMOS, which is mostly used for soil moisture analysis. We have the METOP, which is also used for meteo data sensing, and also Sentinel-3. So all these can be, we have some to be passive and some to be active sensors, which provide us with imaging of the earth, the ocean. Some are able to give us a sea surface topology, topography, and all that. And they are very helpful for sensing images for our analysis. I'll briefly talk about the two most important or popular ones, which is mostly used: the Landsat program by NASA and USGS, and the Copernicus program by the European Commission. So the Landsat has been one of the continuous data acquiring satellite mission, giving us moderate to high resolution land remote sensing data, and started around 1972 up to date. And there are several missions starting from the Landsat 1, and currently we have the Landsat 9. Some of these missions have ended, and the others which are in continuous, providing us with data. And we can access Landsat data from these sources: the Earth Explorer, the Glovis, we have Amazon, and also the Google Earth engine. Also, the Copernicus program, which was designed by the European agency, has 6 missions planned, from the Sentinel-1 to Sentinel-6, which we have some to be radar and optical. Mostly all the Landsat missions are optical, that is the passive sensors, but the Sentinel provides us with some active sensors, some radar data set, which is giving us footprint in spatial spectra and also temporal resolution. One thing about the Sentinel program is mostly we call them the twin satellites. They have, for each mission, there are 2 satellites that are being launched. One goes and the other follows. So they're able to give us a shorter temporal resolution, or the revisit time is also short. Whilst Landsat may be giving us a 14-day, Sentinel can be giving us up to about 5 to 8 day temporal resolution. And similarly, they can be also accessed from some of these lengths. Now, once we're able to source or download these data sets, how do we visualize? How do we process them to make them useful for our analysis? So we have some commercial softwares like the AirDAS, MapInfo, MV, ArcGIS. And with this, we can process the data, we can correct the data, we can manipulate the data and use it for our analysis. Shift from commercial to open sources provides us with other softwares, which is mostly used by larger communities and forums, and mostly for developing countries. And these are examples of them. We have the SNAP, which is mostly designed or purposely designed for Sentinel applications. We have the Quantum GIS, we have the MapInfo, we have the Multispec, Airways, and R. And lastly, the Google Earth engine, which was provided by Google. So with the Quantum GIS, it helps us in the integrating of several open sources. Because it's open source, the community is able to provide us with several plugins that can be used for analysis. So we have the SDP plugin, which is semi-automatic classification plugin. And this plugin handles almost all the images or satellite missions that I have talked about in terms of downloading the data, in terms of pre-processing the data, and a whole lot. The QGIS also provides us with powerful graph routines, such as the ATCore, which is used for atmospheric correction of the data sets. We also have a high-level topographic analysis, making possible using the Saga GIS. We also have GDAL routines that permit us for projections and geoprocessing. We can also have non-parametric classification routines available so that we can perform some segmentation. And lastly, since it's an open source, we have the possibility of building our own routines or models to incorporate and use. The Snap also provides us with similar ones, which is solely for Sentinel and other data set applications, which goes through pre-processing routines like the radiometric correction, geometric correction, maxing, subsetting, and reprojection. We can also extract some indices as we talk about vegetation characteristics. These indices can be also extracted from using the SNAP, such as the NDVI and the SAP. Some biophysical parameters can also be extracted, such as the leaf area index. And Sentinel has a toolbox called the BEAM. This can also be used in water quality analysis, and some parametric and non-parametric classifications can also be done. One other tool which is being mostly used is the R. The R was originally designed for as a statistical application tool, but now it's able to handle image analysis and GIS analysis. So R has several packages that can be used for image analysis, such as the R toolbox, the MODIS toolbox, which is solely designed for processing or pre-processing MODIS data set. We have the Landsat, which does radiometric and topographic correction of Landsat data sets. And we have some models or packages for visualization, some for handling the data set and image processing. One of the powerful applications nowadays is the Google Earth Engine. This Google Earth Engine is a computer-based platform for running geospatial analysis on Google infrastructure. And it has a code editor, it has the data explorer, data catalog. So the code editor is a web-based for writing scripts, JavaScript for running all the processes that we can talk of when we are looking at remote sensing data set. The Explorer helps us a web page to explore all the data catalog that the Earth Engine provides. So there are chunks of planetary scale platforms that provides us with Earth science data and also analysis. Some are derived data sets that we can download. Some are primary data sets that we can download. And we have about 40 years of historical scientific data, and it's being updated daily and it's being expanded. So we can download Landsat, Sentinel, MODIS, ASTA, SLTM, and several other products from Google Earth Engine. One thing is that with the previous applications, you may have to download the data from the source and now work on it. But with Google Earth Engine, you need not to download. You can work everything on a cloud base. Then later you download the results or the product that you are interested in. Now, once we have downloaded all these, we have processed the data and a whole lot of these remote sensing data. Before we can use these data sets, there is another aspect that we have talked about, which is the geographic information system, which is a computer system that helps us in display analysis of geographically referenced information from a variety of sources. So we can be looking at some sources from the satellites, some sources from the drones or the airborne. We can also be talking about terrestrial information, which ones we can be downloading or accessing from other sources, such as the GPS by recording images. Not than that, GIS can also handle textual attributes. So once we go to the field, we do our soil measurements, we'll be calculating our bulk density and our stock. These are all attribute information about a spatial data. And GIS provides the integration and using of all these data sets. So it provides us with a wide range of data forms. And mostly we can group these data as spatial and non-spatial. With the spatial, we can be talking about the satellite images, the GPS locations. The non-spatial, we can be talking about the bulk density, the descriptions that we can give to any study area. So this is how GIS data may look like. So we have the spatial data. This is an example of soil sample locations as a research site. So all cores of soil which were picked can be located, or its GPS location has been stored, and they are the spatial components of the data. So other textual information as the soil weight, the bulk density, the soil organic carbon, and its percentage are the attributes or the non-spatial data sets. Some of the spatial data sets can be the ones sourced from the satellite, and all these have a reference to the surface of the Earth or to the group. That is why we call them geo-reference or spatially referenced data. Now, how do we input these data sets? Because GIS, one of the most important aspects or component of GIS is the data. So we can have the primary data and the secondary data. Once we go to the field and pick our locations, data points, those are the primary ones. That's the ones we have generated. We can have secondary data that we can source from other online platforms, some from published articles, and some from other distributors or our colleagues. Before we can use these data sets, we have to ask ourselves some questions. What the data are required for in terms of boundary location details, in terms of area coverage, in terms of population sample. Once we know this, we know the kind of data we are supposed to go in for. And based on our analysis that we want to perform, at what resolution is the data also required? Are we looking at a small scale or a large scale? The resolution is the smallest discernible units that the representation can contain. So mostly once you take a photogrammic film and you zoom in, the resolution is the grain size that you can see. We can also ask ourselves the accuracy and precision that the data contains or that the data will be needed. So the precision is the closeness, the measure of how close the representation of a world object is located to the original. And the accuracy refers to the correctness of the representation. What data are available? Do we have any previous or historical data? Can we send some from public sources or also published sources? We have to ask ourselves all these questions before we can access these data sets. So if there are some available, we need not to go to the ground to do measurement. So if we want to measure or have some of these data sets, we have to understand some of the data types and its representation. So all that we are talking about, climate, topography, soil organic carbon, soil type, they can be all termed as geographic phenomena. So a geographic phenomenon is a manifestation of any entity or process that can be named or described, that can be georeferenced, and also that can be assigned time interval. So at a point in time, we can tell that we had this amount of soil organic carbon. In the data assessment or report, we can talk about the data and its integrity. So these geographic phenomena can be classified into two. We have the field and also the object. The geographic objects are mostly objects or entities that do not cover the entire study area. There are some spaces in between, which is sort of potential, empty, or undetermined. So some examples are roads, buildings. at some point in time, road doesn't continue to all other places within a steady area. We have its limit, we have the boundary, so it can determine that we have the width and also the length of the road. Outside the road spaces are potential empty or undetermined spaces. So these are called the geographic objects. They have definite boundaries that can be determined or measured. Aside that, we have the geographic fields. With the geographic field, every point in the steady area, we can determine its value. So for this example, the image on the right, each point we can estimate the height at that location. So for geographic fields, we are looking at elevation, temperature, barometer, and pressure, barometric pressure. And within the geographic fields, we can have two classes, the continuous and the discrete field, The continuous fields, it means that all changes in the fields are gradual. So example, slope, we have the slope at each change of elevation. They are gradual. With the discrete, we can have subparts within the steady area, within the space. And for each subpart, the locations of the entity can be measured at each place or at each point. So for example, if we have a land use classification or land classification or vegetation types, we can have spaces where agriculture or farmlands are. The farmland may extend from one point to the other. One is terminated, you go into the forest. So these are some of the discrete fields that we can have. So this is an illustration of the type that I've mentioned, the fields and the objects. And within the fields, we have the continuous and the discrete. And these are some examples that we can have. So land use that we may be working mostly with is a continual, it's a field object, but it's a discrete. Temperature is a continuous field data that we can be using. And based on these data types, they have its representation. Once we know that this is a field and it's continuous, how it's being captured into the GIS is also key. So we'll quickly look at that. And in that, it brings us with two major data models. We have the vector model and also the raster model. So the vector model is mostly for objects, geographic objects, where objects are being represented as points, line, and polygon. So for example, if we are collecting soil sample locations, those are geographic objects, we are picking them as points. But later we may want to translate or transform that into a continuous surface because the phenomenon that we are going to describe is in entirety is a continuous field. So, but we begin from the vector model by representation of points and later transform them to the raster surface. So the raster is also a set of regularly spaced cells with associated values. So each cell has a value which is representing reality. So if we have buildings, vegetation, different kinds of vegetation, they all will be having values or field values that will describe the phenomenon at regular grids. And the grids can be high resolution or low resolution. So when we talk about high resolution or spatial high resolution, it means the grid sizes are very small and it's going to give us final details. But when we talk about low spatial resolution, it means the grid sizes are quite large, from about 100 to 250 meters square. Now, with these data sets that we have talked about, we have mentioned for soil carbon measurement, we will need GPS locations of the sample. We also talked about we can also be sensing remote sensing products or area-based products like the drone images. Once we have some of these data sets, they have to be integrated. But the integration of these data sets, because they are spatially referenced, they have coordinates assigned to them or coordinate systems. So in some events, as I've mentioned, we can source some of these GIS data sets from public spaces or online from other colleagues and all that. In integrating, there is a common problem that can be found, where once we superimpose the vector data on the raster data, they may not be aligning at the same location. So we need to georeference them. In georeferencing, we are assigning the true coordinate value to these images. So for example, as depicted, we have two drone images that have been imported. One is rectified and is showing the exact location as the data is. And the other, the EV004 is the unrectified image. So you can see that there is a little bit of shift in the data set. So once we occur or we have some of these challenges, it can be rectified by these two processes, rectification and registration. They are quite different, but they can be used interchangeably. So in the rectification, we are arranging location of object to correspond to a specific reference system. And mostly we are talking about the geodetic reference system. But in the registration, we can be registering or rearranging locations to one set so that they will correspond to the data that we have, another data which we may not be specifically referencing it to a particular reference system. So these are the two differences between the rectification and the registration. Now, with this said, it means once we're able to have this data, we have our data points, our images corresponding at the same location. It means we are good to go, and any analysis that we make will be accurate. Once we are done with the data collecting and processing, we look at the soil carbon modeling approaches. So in modeling approaches, we can be employed to predict potential changes in soil carbon reserves as land use and management practices changes. So in certain areas, it may be difficult to estimate the carbon. In such areas, that is where we use environmental variables, land use and management practices to also help in the estimation of soil carbon. So basically, there are three categories that we can have for estimation of carbon stock and exchange. First is the empirical or data-driven. We have the process-based or mechanistic. And the second is a fusion of these two, where we can fuse these two empirical and data-based models. So this is the three types as I've mentioned. The empirical model mostly does with initial measurement or baseline measurements, and other several environmental covariates that we can have, such as NDVI, climate, and other factors. With the process-based, it has to do with the mechanism that goes inherent within the soil from the transfer to the storage of the carbon or activities, land management practices, climate and soil moisture activities are all mathematically represented in the process base so that we can quantify or model the soil carbon. And the meta one has to do with combining these two models to give us another estimation. So quickly, let's look at some of the empirical models that can be used. And this model mostly do with a link between the carbon drivers and the baseline starting carbon stocks. So these models, as I mentioned, does not necessarily consider the underlying process governing soil carbon stock dynamics, but is mostly rely on statistic correlation. So in such, some of the environmental variables can be NDVI, rainfall, temperature, land cover over some period of years. The digital elevation or the topography can also be included, and various indices from remote sensing products. Farming techniques or measurement can also be drivers of this carbon, so they can also be incorporated. This model is mostly simple to create, but it takes data for us to generate these models. And we have a range of methodologies that we can use. And mostly we can be looking at the most simpler one, the spatial interpretation, regression, machine learning, and deep learning can be applied in this empirical model. With the spatial interpolation, is a process of using points with known values to estimate values at other unknown points. So once we do a field measurement, we record carbon stocks, we take the core, we do the laboratory assessment and assess the density and the stock. We also have the GPS locations of these stocks. The carbon stocks that has been estimated from the labs serves as attribute information, and within a GIS platform, we can perform this interpolation to estimate for the entire study area how the carbon stock is being distributed. So this is more computer-based, and this is an example of temperature map interpolation from South Africa weather stations. So all the continuous fields that we can talk about, the rainfall, the temperature, the soil, water quality, and all these, we can pick their district form as grid points or random points, and we can interpolate and get this continuous form as field. There are several interpolation methods that can be used, but I'll mention a few. We can also look at the others. So mostly we can be looking at the nearest neighbor, the IDW, the inverse distance weight, the triangulated area network, and Kriging. There are several Kriging that can also be available for us. The simple, ordinary, universal, regression Kriging, all can be used in interpolation of these data points. With the nearest neighbor, it assigns the value that is most closest or nearest to the observation of a particular grade node that we are interested in. And mostly this is limited to continuous field. Once we want to do a continuous field like the temperature, rainfall, we are limited in such using the nearest neighbor. This is best for qualitative data interpolation, such as land use classifications can be easily done using the nearest neighbor. The inverse distant weights is an advanced form of the nearest neighbor approach, which include more observations that are closer to the unknown location that we want to assess. So mostly a value, if you want to assign a value to a particular grid, it obtains a linear combination of all nearest neighbor stations and estimate a weight also for the observation based on the distance between the station and the unknown points. And these weights are included in the estimation of the unknown locations. And mostly this works well for regularly spaced data sets. So if we have a field that we want to interpolate the soil organic carbon, it means we can go by the systematic grid sample where we can have regularly spaced data points to use IDW to generate the surface. And also we can be using Kriging. Kriging is a geostatistical interpolation method that considers both the distance and the degree of variation between the data points when estimating unknown areas. And we can leverage on the simple, ordinary, and universal Kriging. So these are some examples of interpolation application that has been used in soil organic carbon. So in this study, soil organic carbon was estimated for a particular study area using IDW and also ordinary Kriging. And there are some differences. With the Kriging, it has to satisfy an assumption where the data points should be normally distributed. So in such cases, we check the data points and use as such. Interpolation of elevation surfaces can also be done in the case where we do not have a digital elevation model and we have data points. As I mentioned, there are several sources where we can get these spatially referenced data. So if we have elevation data points, we can generate our own digital elevation surface to incorporate in our estimation. Other concentration surfaces can also be generated using interpolation. So let's quickly look at a case study which uses regression approach in estimation of soil organic carbon using remote sensing and GIS data. And this study leveraged our programming tool for the study. So with this, first we talk about delineating or assessment of the boundary. This boundary was delineated using a river basin. So if we are lucky to have the shape files of the river basin from a colleague or from an online repository, but if not, GIS applications can help us to generate these basins through several other processes that we can look at later. So in this study, a field measurement was done where random sampling was used to collect soil cores at a depth of 0 to 15 centimeters. Whilst doing that, a portable GPS was used to collect all spatial locations of each of these. Without you having a handheld GPS, we can leverage on mobile phones. All these smartphones have GPS that can give us also up to about 3 to even sub-meter accuracy, and they can be used using other third-party apps like the GPS Essential and Mapit. Once the soil samples were collected, field or laboratory assessment were done to estimate the bulk density and also the soil carbon using these equations. So summary of the field sampling can be tabulated in this form, where we have the sample unit, we have the geographic location, the latitude and the longitude, the weight, the soil weight, bulk density, and the soil organic carbon. This is what we call the attribute information. And these will have a spatial bearing, and that is the geographic location that we have. This data will now be plotted in any of the GIS applications, as I've mentioned. But in this study, the R programming language was also used. Remote sensing data leveraged on the Landsat imaging, which was used to estimate the soil organic carbon. So for digital soil mapping, these environmental variables are important. In this study, only vegetation characteristics was used, but we can inculcate topography, we can inculcate soil type, we can inculcate climate characteristics in all these studies. But here the study looked at this distribution in relation to several other vegetation indexes. Near normalized difference vegetation index, the rate normalized, we have the SAVI, which is a soil adjusted vegetation index. And these are some of the indexes. These indexes is a ratio of the bands that are being sourced from all the satellite missions that we talked about. So the hyperspectra, the multispectra have several bands that are being recorded, and each band stores information for a particular wavelength, ranging from the visible to near infrared and near shortwave infrared. So these band ratios can be performed on them. So for the NDVI, we can have a ratio of the near infrared minus the red divided by the near infrared plus red, which will give us an indices. And this indices ranges from 0 to 1, which talks about some particular characteristics of the vegetation type. And this is mostly used in estimation of biomass and the vegetation production. So these are the details of the predicted variables. So once we generate the indices, these are the results from the indices. And all these are layers or georeference data sets that can be used in estimation. So it goes through a flowchart where the data, satellite data are collected, the field sampling are collected, we do some thresholding. The vegetation indexes can be threshold because we have, once we generate, there are certain values that represent some features on the land. Crop lands will have a particular range where Forest areas will also have a particular range. Water body will also have this range. So we can have a threshold to segregate or classify the various vegetation within our study area. And a regression using the R models can also be performed to aid us in our prediction of soil organic carbon based on the soil samples that has been collected. So normally in the statistics, GenStats is a package for within R that can help us with the descriptive statistics. We can also have the LM function, which is a linear model function that can be used to perform simple and multivariate regression. Kriging, ordinary Kriging, random forest, all the machine learning algorithms can also be implemented within R. So depending on your knowledge, we can implement all these models, empirical models within R, and all other software that I've mentioned, the quantum GIS, the ArcGIS, that is a bit simple. There are clickable buttons that we can just click and input our parameters and they will be calculated for us. But with the R, we may have to script and write the code. Once those the prediction have been done, there's an assessment that can also be done on the accuracy of the prediction of soil organic carbon. So mostly the root mean square error is used to assess how accurate our data set or our prediction is. And we have the normalized one, which aids us to compare several other models. And the mean absolute percentage error gives us the error or the accuracy in terms of percentage, so that it can be simply interpreted by the layman. So this is a result of a spatial prediction of soil organic carbon using a multivariate regression. So this combined all the indices or all the covariates that is we have assessed from remote sensing data sets, and it's used to estimating the soil organic carbon. We can also do a linear model where we use each of the indices to predict the soil organic carbon over the study area. Now let's quickly look at also the process-based models, which is mechanistic and it simulates the intricate process responsible for soil carbon turnover. So with this, all the underlying dynamics that governs soil carbon storage is being represented as mathematics or equations to help us in estimating or generating a model for our carbon storage. So the process-based, mostly we can extrapolate or project across complex landscape, and mostly requires a high resolution or medium to high resolution of less than 250 meters squared. And this is mostly dependent on the data availability, extrapolated, and also the spatial resolution data for our calibration. There are several of these process-based models that can be used. But before we make a choice of the one to use, we have to look at the objective, the data available, the time necessary, our computer capability, and some technical competence. For this requires a lot of parameters to be inputted. And all these models can be also utilized at plus scale, at a regional scale, where we are incorporating GIS functionalities. So some natural resource managers can use and policy analysis. So in order to also get the land use management practices or the farming techniques, these can be sensed from a remote sensing base. So these are some common 5 process-based models that can be used. We have the model, the website that we can access it, and the notable features, the timestamp that we can also use it, the input parameters that is needed for the model, and also the outputs relevant to soil carbon. So we have the RODC, which is fairly user-friendly and can be run in the forward and also the inverse models. And this is mostly done on monthly data sets. So if we have monthly climate data, rainfall, air temperature, and evapotranspiration, all these monthly data set, as I mentioned, satellite products that are being launched in space or missions, some are able to provide us daily observations. Some are able to provide us within 14 days, it can give us information at a particular scene. Some are also able to give us monthly. So some of these products can be sourced monthly from the sources that I mentioned. Most importantly, the Google Earth Engine. We can source all these monthly rainfall and temperature data. Soil clay, we can have access to soil data, global soil data that we can use in these analysis. We have the Sentry data, which is widely applied in ecosystem modeling of carbon and nitrogen. And this can use the daily or the monthly data set. So we can source all these things. So before you can use any of these, we have to check the input parameters and get access to all of these. Some are able to use the land use type. In such cases, we have to get our Landsat data, Sentinel data, and do our classification of this land use type and incorporate it. Some of the land use type can also be downloaded from online repository where global land use or land cover changes have been also performed for certain areas. Once it's for within our area, we can download and assess the quality or validate our data, and we can use them. So some are able to provide us with soil carbon and also carbon dioxide flux. So with respect to the output that is required, we also choose appropriately. So in ending, there are some hands-on practicals that we can look at in soil carbon measurement using geospatial techniques. So there's a link which can help us to assess data in tutorial on mapping soil organic carbon using soil samples and derive organic carbon stock using soil profile data. So we can assess, and this was implemented in R. So we can, the codes are there, we can perform them and see how the visualization, how the models are being provided or produced. There is a second part which we can also look at if we have access to multispectral UAV platforms. We can also map certain area and collect samples for a particular farm and also generate our own empirical model to estimate this carbon. Okay, so this brings us to the end of the fourth section on soil carbon sequestration using remote sensing and GIS techniques. Thank you.
Thank you very much, Da Costa. William, do you have anything else to add?
William, do you have any correct?
Hello.
Yeah, yes, William.
Yes, we can.
Wilson.
Oh, yes, Prof. Ajari.
Yeah. So now at this point, I think we'll take some questions, interactions, and then.
Hello.
Hello.
Yes, thank you so much for once again the very in-depth presentation. A lot of learning has been transferred. My question, I think, is general. There are a lot of practical aspects that require perhaps physical interaction with some hands-on practical exercises. I'm wondering how RUFORUM could help to facilitate a physical meeting. I don't know whether they are planned for it. Otherwise, when it comes to our institutions, it may be very difficult to deliberate on some of those aspects which required hands-on, which were only mentioned, but we understand the process, but the in-depth aspects required perhaps a physical presence and interaction with the facilitator on a software. I don't know what Rufaram has around that for us. Thank you.
Yes, Francis, thank you. We will I'll pass on the message to the leadership of the program, and we see what is possible. Because all this requires really funding to support the workshop, physical workshop, and also to transport the facilitators. So I think it is something we shall look into. I know Pascal is planning some similar physical trainings in the universities in West Africa. So we will see what is feasible in terms of that.
Thank you.
I have a question before. A question. It's about the random sampling you're talking about. How do you make sure that your soil's random sampling within a given country is representative of the entire country's soil carbon sequestration, taking into account that the soils are for different patterns in different locations? Thank you.
I think when it comes to sampling soil, if you are considering the scale of the country, you cannot just a random sample and then get it right. What you have to do is first, there is already ample knowledge in all the countries we are dealing with. First, you may have to zone into soil type, then you can now sample within them. Otherwise, you might just do random and you might not be able to cover all. So once you zone, depending on the sizes of the various soil types you come up with, and then your resource will also, because soil analysis is quite expensive. So depending on your pest, then if you have the capacity to, let's say, analyze 300 samples, then you will share it based on the sizes, and then you can now come into the randomization. But just throwing the random point will not be. First, it should be strategic. You zone based on past knowledge, or you can also zone based on the vegetation or climate or something, and then you now go in, not just from the beginning randomize.
Okay, thank you.
Any other? If there are none, then if there is none, then we will move back to David for the closing. The chapter.
All right, thank you very much, Pascal, and especially our facilitators. I think the training has been very interesting, and especially for the lecturers who are in the field of soil science, they'll find this really refreshing for them as well. And I think they have picked some new elements that probably they didn't have in their own courses and programs at the universities. I would request that participants complete the evaluation form. That will also constitute the attendance registration for today. I would also want us to just take a group photo, so everyone can put on their videos, and then we take a group photo.
Me, the link is not opening for evaluation.
I think it opens. I don't know whether it's the same thing with others, but I think it works.
You may need to check on your 4 times.
The browser. You might need to check on the browser.
It is using Firefox.
Yes, me, I use Google Chrome. I don't know what's the experience with others.
I'm using Google Chrome, but when I click on it, it goes to Firefox.
No, then look there, close. Close.
But yesterday it was very fast in opening.
Dr. Mulebeke, mine has opened. I don't know what's
I don't know
happening to
also,
yours.
yes, it could be an issue with the computer, the browser. Maybe it needs to update the settings or something like that.
Mine also worked. I've already completed.
Okay.
Okay. I still see some people have not opened the videos.
Maybe they left their Zoom on.
Dr. Mulebeke, we can now see you.
Thank you, thank you.
You can come here. Come here.
Okay, I think other people's videos cannot open. I think at this point, I would want to welcome Prof. Kone from Wascal to give really the closing remarks for the training. Thank you very much, especially on behalf of the Forum Secretariat.
Okay. Good afternoon, everyone.
Good afternoon.
Good afternoon. Good afternoon, team of Wascal over there. Massive. Thank you so much for the great job. So, good afternoon, David.
Yes, Prof. Good afternoon.
Thank you
very much.
All the people who are in a platform are lecturers. They are thank you so much for attending this 3 days training. It was a training of trainers. That's why you are trainers. I think our forum is going to issue the certificate for all of you. We want really to appreciate your time coming to listen Wascal team, sharing what they have developed in terms of carbon sequestration with all of you. We want also to say big thanks to the forum for making this, for facilitating this also, and also for the big collaboration with Wascal. This is just a starting point also, I can say, because we have additional courses coming. I think David did a great job. I want to congratulate him. I want also, he will continue sharing with you any upcoming training based on what your interest in those training. I think we'll be happy to see all of you. Thanks the leadership. I've seen the day before yesterday, Sokona came to some remarks, and also Florence was online, Majaliwa, all of them. Thank you so much. So, congratulations for this great job, and we are really seeing how now we can also go ahead, because we need before to go ahead to finalize everything to get the feedback from the those people online. Please feel free to send your comment, how far you want this thing to be improved. David will collect all of those information for Wascal team to put this into consideration before the final document will be ready and shared with the forum. Because at the end, the document will be on a Reforum platform, but we need also your additional comment link to David will collect all of those comments, and we share with Wascal. Wascal will consider this in the final version of the document. And also we are organizing some event in Wascal side. We will let David know. Maybe we cannot bring everyone on board on site, but we see how we can also connect some of you during this time if there is any practical activities. So thank you so much, colleague online. Thank you also for the team of Wascal in Kwame Nkrumah University, and also the lecturer at the Kwame Nkrumah University who also did a good job. Thank you, David, and thank you all for this sharing activities. So on that, I will say close this 3-day training of trainers under the leadership of Reform and Wascal. Thank you so much.
Thank you, Prof. Bye to everyone. Please continue providing your comments on the survey that I shared.
Thank you so much.